Welcome to the presentation of our paper in which we show that camera poses alone can be enough to infer the 3D layout of a scene. Visual localization is the process of finding the pose of a camera corresponding to an image in a coordinate system that defines the 3D scene. A client-server based localization setup where the client captures an image and sends it to the server that stores a scene representation for computing the pose is practical for applications running at scale. This leads to privacy concerns related to user content in both the query images and the stored scene representation. Recently, several privacy-preserving representations have been suggested for both these possible privacy leaks. In this paper, however, we show that even when using such privacy-preserving representations, a localization algorithm is susceptible to privacy leaks via the computed camera poses. We show that an attacker can use images of commonly occurring objects to query a localization server and use the obtained poses to infer details about the scene, such as the objects present and their positions in the scene. So this was the broad overview, and now we'll go into more details. I am Kunal Chirani, and this is the presentation for our CVPR paper titled Privacy Preserving Representations Are Not Enough, Recovering Scene Content from Camera Poses. This is joint work with Torsten Sattler, Frederick Karl, and Zuzana Kukilova. In a client-server based visual localization system, privacy concerns related to the user's scene have recently gained increased importance. The problem has largely been studied from two angles: preventing privacy leaks via the query images and via the scene map stored on the server. Methods based on obfuscation of geometrical primitives, modification and sparsification of features have been suggested to prevent recovery of user content. In this paper, however, we provide a novel angle to the problem of privacy preservation in localization. What can be inferred from just the camera poses that are returned to the client? The motivation for analyzing this angle lies in the observation that most state-of-the-art localization pipelines and their components are designed with robustness in mind. Robustness to changes in appearance, lighting conditions, geometry, etc. Although this is a desirable attribute for practical localization systems, it also allows finding matches between images that are not from the same scene and enables localization of images of similar-looking objects across different scenes. With this motivation, we propose a scenario where an attacker acts as a client and is able to query a localization server with its own curated set of object images. By developing a proof of concept attack pipeline, we are able to show that irrespective of the localization algorithm on the server, by using only the minimal information of camera poses, an attacker can actually infer objects present in the scene and their positions. The simplest form of such an attack would be to send a single object image as query and use the pose returned by the server to infer the object's position. However, an underlying practical assumption is that the localization server tries to align all query images as best as possible and hence returns a pose for every image. This results in two major challenges to this simple attack. First, since every image gets a pose, it's impossible for the attacker to infer which object is present and which is not by sending a single object image. Second, for an object class that is present in the scene, the returned pose by the server can be quite noisy due to the possibly large differences in appearance and geometry between the query object and the one actually present in the scene. Noise in this pose would here mean that it is far away from the concerned object or not pointing towards it. To overcome these challenges, we suggest that the attacker can implement a strategy of using multiple images of each object captured from different viewpoints. The idea here is that some of these viewpoints would hopefully align well with the scene and would lead to providing appropriate cues to position the object. This would overcome the second challenge. Also, the distribution of these poses can be used to reason about the presence or absence of the object in the scene, overcoming the first challenge. Here is the suggested attack pipeline in more detail. The attacker has a database of objects, each object having a set of images from different viewpoints. These are used to build a 3D model using structure from motion and thereby providing a set of camera poses in a local coordinate frame, the local poses. The attacker queries the localization server with a set of images and obtains a set of poses in the server's coordinate frame, the query poses. These two sets of poses can be aligned to position the 3D model of the object in the server's coordinate frame. We suggest a robust consensus-based method to align them. More specifically, for each pair of corresponding poses in the local set and the query set, we obtain the transformation that aligns them and then count the number of corresponding pairs that agree with this transformation within given thresholds of rotation and translation. We average over the transformations from the best inlier set to obtain our final estimate. The attacker now has a way of computing object positions, and the remaining task is to classify the attacking objects as present or absent in the scene. For this argument, that the relative query poses of an object that is present in the scene would align well with the relative local poses, and those of an object that is not present would be rather randomly distributed. We suggest that the inlier ratio from the pose set alignment method captures this quality of alignment and can be used to decide an object's presence in a scene. In practice, we observed that a single threshold is not sufficient to accurately decide the presence or absence, as this depends largely on the object's and scene's appearance. We therefore suggest learning such a threshold for each object using a set of training scenes. We now move on to discussing our results. The first dataset that we used to validate the attack pipeline was curated at an IKEA furniture store. In this dataset, the inspiration room setups at the store are used as server-side maps, and the video recordings of few objects from the inventory section were used for attacking. We used HLOC, a state-of-the-art localization pipeline, to emulate the localization server and also analyze results over 3 different local features, namely superpoint, R2D2, and SIFT, to weigh them on the scale of susceptibility to such an attack. We made the expected observation that learning-based local features such as superpoint and R2D2, which are quite robust to changes in scene conditions, are also more susceptible to this kind of an attack. Here is an example result showing the obtained object positions overlaid on the underlying server map in gray. Please refer to the supplementary material for several more such results. To show that the attack works by using images of similar and not exactly the same objects of a category, we also present results where an office scene from ScanNet dataset is used as server-side map and recordings of common objects from our own scene are used for the attack. As can be seen in the alignment, the scene layout is faithfully predicted considering the minimal information being used. The task of deciding object presence from camera poses is a rather difficult one. Our suggested method is not perfect, but produces reasonable results, and the underlying motivation definitely holds. To further analyze the feasibility, we discuss a simple defense strategy of rejecting localization if the 3D point inliers in geometric localization predominantly come from a single object. Here, the dashed bars show the fraction of rejected malicious queries, and the undashed bars show the fraction of rejected genuine queries. As can be seen, such a strategy would reject service to a significant fraction of genuine queries too. To conclude, in this paper, a novel privacy attack via camera poses in client-server-based localization setup is presented. A proof of concept attack pipeline is implemented to show the feasibility of the attack, and 3 different local features are weighed on the scale of susceptibility to such an attack. It is shown that it might not be trivial to develop a defense without affecting the robustness and reliability of the localization service. Finally, we conclude that more research in the direction of privacy-preserving localization is definitely needed. Please visit our poster and GitHub page for more information.